Hello, everyone. So this is the third edition of research paper with the author, and today I'm very honored to have Max with us. So he worked on swarm parallelism, which is like a kind of like a pioneering paper for decentralized training regarding the model parallelism axis. And so, yeah, I'll let you introduce yourself, Max.
Yeah, sure. And thanks, Fernand, for the introduction. My name is Max. I am currently a research scientist at Together AI. I work on large-scale deep learning, and I did like I was happy to contribute a bit to the field of decentralized deep learning back during my PhD. We made like several different we tried to make a way through several different research directions while working on that big problem, trying to understand how to train on poorly connected and unreliable devices over the world. And swarm parallelism was our approach towards training very large models when you don't have a lot of like server grade GPUs connected with high bandwidth.
Okay. And so the way I see it right now, when people try to solve the decentralized training field, is like there's different axes to solve it. The first one is doing like DDP kind of approach, like DLoco and stuff, with Arthur Douillard approach. Some other people try to tackle it through the optimizer level, like new research and stuff. And the other one is actually the model parallelism one, with like Swarm. So I wanted to ask you, what is the motivation to go through this route compared to the others?
Yeah, sure, and thanks for the question. So basically, the idea behind the approach was that before swarm parallelism, we were trying out different ways to go decentralized over the data parallel direction. So in particular, we conducted our first like serious real-world experiment here with our paper called Distributed Deep Learning in Open Collaborations along with some folks from Hugging Face, by the way. The method is named deadlock, and the idea was that we could exchange, we could just create, uh, use very large batches for
Mhm.
data parallel training and have an adaptive procedure which can basically allocate the work to each peer, both for computation and for communication, depending on how fast they are. So this approach was proven to be working in practice. So like we conducted an experiment with people joining even from Google Colab, which is very fun, if you ask me. But the natural limitation of data parallelism, unless you are willing to do stuff like FSDP, is the scale of the models that you want to train. And of course, we want to like leverage all of the compute we have, not just to train models at a small scale, but also to improve, like to push the state of the art and ideally train much larger models. So naturally, we came to model parallelism, broadly speaking, as a research direction, and we started thinking about like how we can actually make it work in this very weird setup when your network connection speeds are like several hundred megabytes per second, and you cannot guarantee that anyone in your network will stay there for the whole run. So yeah, that was the idea behind swarm parallelism. At least that was the big research question behind swarm parallelism.
Okay, so I guess you cannot like apply traditional pipeline parallelism directly to this decentralized training setting. So can you like, for example, highlight the following, I mean, the main contribution of this paper? Like I see this like in this page, if you page two, I think.
Yeah, sure. So I would describe it as follows. Like the first one is that we try to take a look at like the way different model parallelism techniques work. Not
Mhm.
FSDP because FSDP was still fairly novel at that point. And we made an observation, which is like in hindsight very simple. I would say that like different approaches in the past try like made very similar conclusions. It's basically an observation that when you train larger, wider models, in particular more compute intensive, you can kind of hide the communication overhead because you spend like more time asymptotically on compute than on sending over the activations. So that was the general idea that inspired us to go into the direction of pipeline parallelism in particular for
Mm.
this distributed setup. Next, we took a very close look at the conditions in which we operate. And as you can guess, no prior solution for pipeline parallelism, even at the algorithm level, actually considered that you can be using like different GPUs. Let's say someone joins with a 4090 and someone joins with an H100. So you want to leverage the compute resources for all of them, but obviously those GPUs cannot do the same type of work. Or if you just reduce it to the lowest common denominator, it's going to be much less efficient than what you'd have. So with those constraints in mind, as well as with fault tolerance in mind, we decided to develop swarm parallelism, which kind of addresses both of the problems that I mentioned to you. So everyone can disconnect, everyone has different speed, both for network and for compute. And yeah, basically our latest, like our last contribution for that work was to show that it works at the scale, like which is relatively modest at this point. So it's like a few billion parameters unshared, and like with in compute it's equivalent to 13 billion. But given the all other challenges that we solved, that was basically our main focus at the moment.
Okay. So yeah, the square cube law is interesting. Can we go on page 4? I have some question regarding the square cube law because if the computation are growing, I mean, it's um, sorry, that we spend more time doing computation than communication, then why not, for example, go for tensor parallel, for example, instead of pipeline parallel?
It is true in
In
principle.
theory, yeah.
Yeah, like in principle, like you could think about tensor parallelism, but the problem is that with tensor parallelism in particular, your requirements to send, like to communicate the data, to exchange those activations are a bit different. It's I would say it's a question of when those communications happen. So, like with pipeline parallelism in particular, it's relatively independent across layers. So obviously there is a lot of caveats, but if we view it from a simplified perspective, you could say that every part of your pipeline could be doing some useful work independently because you can slice your big batch size into micro batches. So your whole layer kind of like your whole model, your whole network, GPU network is utilized at any certain point and at any given point in time. With tensor parallelism, however, it's a bit more difficult because if you want to do a forward pass with a model that was sliced via TP, you kind of have to necessarily wait for the activations for the other half or like other quarter of your model to arrive from other peers. And in this setting, you cannot even guarantee that this will happen because let's say I have 4 GPUs trying to do one forward pass, which is sliced across this like activations axis. You're sending those activations, and then one of the peers just dies or disconnects. So in the worst case, you kind of have to rerun the same sort of tensor parallel computations with a different set of peers. So it becomes a bit more difficult because you like kind of everyone in your network is dependent on those results. Also, the problem with TP is that unless you go very wide, it might be difficult for you to scale a lot across that axis. So you kind of still have to leverage other dimensions. And because pipeline parallelism is a bit more resistant to such conditions, or it's like a bit easier to adapt to such conditions. This is the reason why, for example, people usually do tensor parallelism within the node because it
Mm.
has like the fastest interconnect and less fewer things can go wrong. and they use pipeline parallelism across the nodes if it's necessary.
Okay. Yeah, so maybe I think it's time to introduce a bit about like the actual inner working of swarm parallelism. So maybe the figure, so where's the figure? Yeah, it's the figure 2 that explains the thing. Uh, so like for a complete beginner, what was the thought process from like going to traditional pipeline parallelism to actually, for example, having this many
Mhm.
replicas and stuff like?
Yeah, sure. So basically, let me try to first explain how pipeline parallelism works.
I am cool.
Or like, yeah, in case someone is not fully familiar. So basically, we want to train large models. That's one thing. We want to make sure that like each model, each GPU does not run out of memory,
Mhm.
but we have a very like big model, for example, a very deep model with uh, like tens of layers and so on. And you cannot fit all of them on a single GPU. So you cannot go the data parallel direction. Sometimes even going the fully sharded data parallel direction is difficult because of a variety of reasons. So one thing that you can try is basically slice the stack, like the sequential stack of your layers into chunks and put different subsequences, different chunks of layers on different sets of GPUs. So you kind of have this pipeline where you start with the first, let's say like first 10 layers of your model. They are processed on one GPU group. So here it would correspond to, sorry,
Oops.
different color. How do I undo here? Quick question.
Uh, I can wait. Oops. Oh
uh,
God. Can you Control Z by any chance?
yes,
Oh, yeah. Okay,
I can do
perfect.
both. Okay.
Okay,
Yeah,
perfect.
yeah, give me just 1 second. I will.
You can change the thickness on the
Yeah,
left. Yeah.
yeah, much better, I think. Cool. So yeah, basically here you have one stage of the pipeline, and it will kind of host all 10, like the first 10 layers of the model. Then we proceed to the next one, then we proceed to the last one. Let's imagine that the model was arranged in 3 stages. The same thing happens at the forward pass, like you go 1, 2, 3, and at the backward you go 3, 2, 1. So that's pipeline parallelism basically. The thing about swarm parallelism in particular is that your stages become kind of dynamic in a sense. So we do this because, again, we have faulty or potentially faulty connections at every point. And also we have different GPU sizes or like different kinds of GPU participants. So for example, at stage 2, we have T4 GPUs and A100 GPUs. So they have vastly different computation speed and vastly different capacity. So we should try to adjust to that. Um, and the major differences of swarm parallelism and prior approaches or like standard pipeline parallelism is that we kind of route the activations between layers based on these notions of performance for every individual peer. So the first thing that we do here is called like adaptive rebalance, like it's called adaptive rebalancing. And the idea is that, let's say you have this network of peers, and suddenly one of them becomes disconnected. For example, there was a network outage, or the participant who was the volunteer, they decided to just do something else with their GPU.
Mhm.
The problem here is that, of course, you need to like keep processing the batches, and you don't want the pipeline to be bottlenecked by the slowest stage, right?
Yeah.
So the easiest thing you could do, and that's basically the thing that we've done, is to maintain some level of estimates for every pipeline stage. Basically, how quickly can the stage process the examples at a given point in time. And if there is a sudden imbalance in the network at a certain point because someone disconnected, for example, you can try to do the very the easiest thing, which turned out to work quite well in practice for our case. You take the fastest pipeline stage and you try to migrate a peer from the fastest stage to the slowest stage. In principle, like you have to decide which peer has to rebalance here, but very simply, like you can run some simulations offline to decide like who needs to migrate. So this is basically what allows us to maintain this evenly balanced pipeline throughout the operation of the network. So that's one part of rebalancing. Another thing here is called stochastic wiring, and I can try to show what that.
So wait. So first of all, like we went from traditional pipeline parallel to having multiple peers within stage to for fault tolerance. I mean to solve the fault. I mean to have fault tolerance, right?
Yes, that is true. And I would say this is not just the reason. So
Okay.
usually you don't want to go to have a very deep pipeline. And usually it's not necessary because the models are definitely big, but they are not big enough that you have to put like every single layer on its own GPU. So usually you can, for example, have the pipeline dimension, which has like something like 8, 16, well, depending on what scale your model is, but usually you don't go much larger than that. And the rest is the rest of your GPU fleet is used to expand along the DP dimension or the FSDP dimension. So here you can say, for example, that all peers within stage one of the pipeline, they are all in the same data parallel group. So
Hmm.
that's kind of similar to the 3D parallelism approach from NVIDIA. So they also combine data parallelism, tensor parallelism, and pipeline parallelism. And yeah, in our case, it's kind of like a simplified version with 2D, but it's very naturally extensible to TP and 3D.
Okay.
Yeah.
Yes, it was just like to make sure, like I have everything in mind. So then now you were talking about stochastic wiring, right?
Hmm.
So you were about it.
Yeah. So basically, the other thing here is that you have to think about which peers at the following stages receive activations or gradients for
Okay.
training. Because if you go, like if you identify a specific link through the layers, let's say this one, this one, there is, first of all, no guarantee that this link will be present during the entire duration of the training. What if, for example, this participant disconnects at a certain point? So you have to think about this random like wiring throughout the network. And secondly, you often have situations where you have peers which are just naturally faster than others. For example, here, the A100 peer. Or alternatively, you could have someone with a very fast internet connection who can receive multiple inputs at the same time, process them quickly, and then send them to the next stage. So uh, in the volunteer, in the decentralized setting, no single GPU should be there should be no assumption of like uniformity across the peers in terms of the speed or in terms of the computation performance. So what you can do here is apply some very well-known algorithms from networking, essentially. And one idea that was in particular very appealing to us is the idea of load balancing. So let's say that you have multiple participants here at a particular stage, and you have to decide, like, I am this guy. So who do I send my activations to? I ideally want that peer to process those activations as quickly as possible, right? That's my kind of greedy goal to satisfy. So in the worst case, like the most obvious solution is just to identify the fastest peer. Here it would be the peer with A100s and send all of the activations to them. But you can probably easily understand why this is not going to work, or at least why this is clearly suboptimal, right? Because if
Yeah.
everyone sends those activations to the fastest peer, then quickly it will become overloaded, and
It
the
cannot process. I mean, there will be queuing the the forward and stuff. So yeah. So you should like I usually use like a balancing thing to give to others. Like
Yeah, exactly. So basically, you have to understand like uh, who are the peers who can realistically process my batches in the smallest amount of time.
mm,
And the algorithm we kind of based this idea on, it has a very complex name of iterative interleaved weighted round robin, but the way we implemented it was actually not that complex. Like if you distill it to the core principles. So let's say that on every single peer, you maintain a list of the peers at the next stage. And this list tells you the latency for processing your batches by that
maybe
peer.
maybe there's like a pseudocode somewhere we can like follow along. I think
Yeah,
I,
sure.
th I think there is a
In the appendix, there is something.
appendix. Yeah, I think this is here. So appendix 20. If you can join,
Yes, sure.
this is the one I
Yes,
think.
here it is. Yes. This one is the stochastic wiring algorithm. So basically, I can try to like go through the list here. So the main thing we have here is the priority queue. For every single pipeline stage, we have this priority queue, which helps us identify like which peers are the best ones at the current point. So now let's probably go to the forward pass to understand how the logic works. It's a bit simplified because like usually you want to send activations from the preceding layer, but this one is a bit easier to understand. So you go layer by layer as expected in pipeline parallelism, and the first thing you do is choose a server within a particular stage, or like for a particular pipeline stage. So how do you choose it? Basically, you take a look at the priority queue for this particular list, and then you update the priority in the following way. So you kind of try to estimate the moving average time of your, maybe I should underline instead. You try to estimate the time here for how long it took to process the activations with that particular layer. So that becomes your estimate, your kind of like moving estimate of the speed of that server.
Okay.
And as you can guess, for example, if there are many requests for a particular server, then its queue will be very high. And like in the best case, we will just have a very large delta t here, and in the worst case, we will have a timeout, which means that for some time, or like even for eternity, we will ban that server because it did not respond to our request. And if we ban the server, we have to find some other one to run our request. So this is basically the idea behind stochastic wiring. And yeah, like there is some usually like some initialization with the default priority, but like over the duration of your run, this converges, and in practice we've seen that it can be quite stable even for like preemptible peers. It can be quite stable for those conditions.
So
So
in some sense, you swarm parallelism has like another automatic or naturally learns the topology of the network and to find the efficient way of like wiring every GPUs across stages, right?
yeah, exactly. So we kind of try to like each peer kind of like independently tries to see what's the most optimal configuration for them to send activations to. And over time, because of this like moving average, you converge to a stable topology. Yeah.
Okay. Um, but then there was like after the wiring, there's like another stages. I think. I mean, not the stages, but the rebalancing you were talking about, I think.
Yes, exactly. So, like apart from stochastic wiring, we also have the peer rebalancing. Let me try to open it here. I think there is also pseudocode for that too. If
Oh yeah,
it will be
I think we
helpful,
can.
I think
Yeah, I
we
think it's over there. Oh yeah, okay, 21.
yes, algorithm too. Cool. Yeah. So, this is basically the like somewhat similar to what we just had, but for migrating peers between the stages. So the idea is as follows. Let's define a rebalancing period called T. In practice, like 6 minutes, like 5 minutes, 300 seconds worked for us quite well. So once every T seconds, you measure the queue size for your local requests. You write all of the like queues for a particular stage to a DHT. The DHT is like a distributed hash table, and it's just like a fault tolerant distributed key value storage. You can think about it that way. So we write this pair, or like I am at layer I. I have my load as QI. And next, like once everyone updates the DHT, then you can compute the load for every single stage of the pipeline. Basically, like here, we're trying to identify the maximum and the minimum for all of the pipeline stages. And let's say that we know about the, like, we know that the current stage is the one with minimum load. So like the one that's least busy. We can then try to find the peer with the minimum load and then migrate it to the next stage. So like we see that this peer index needs to move, and then it just downloads the parameters from the peers in that other stage. So if we go back, I guess, to the illustration, you can see that here in figure 2, this orange peer was migrated to stage 2, and it can just download the parameters for that stage from the other peers. This is essentially the idea behind adaptive rebalancing.
But then how many times should we rebalance? Because if we spend a lot of time to rebalance, we lose in throughput. So, but if we never rebalance, that we lose as well in throughput. So, what is the when is the good time or what is the good trade-off to find, I mean, to actually trigger the rebalance?
Yeah, so in like in our case here, we did not see that it's important to rebalance that frequently. So
Okay.
unless you have something very, very random, like half of your network can disconnect at any single point in time, it's usually that your network composition is relatively stable over time for each layer. It can just have like a couple of peers which drop at the very at the particular moment, and like a couple of new peers which connect. And if you have someone who connected, you just naturally connect, like to attach them to the slowest stage to make it stronger. So in our case, in experiments, I think we even saw it
Figure
like,
6, I think. Yeah.
yeah, like in figure 6, we saw the impact of rebalancing overall. So you can see that like if you have multiple stages, then in the worst case, it kind of like goes down on this like very negative trend. So you never rebalance, even if your new peers attach. And this is based on like some real world data with preemptible GPUs, by the way. In case of adaptive rebalancing, it's a bit better. And I think we actually have, if you give me just a second, we have the numbers for pipeline rebalancing. Yes, I think it's table 5, just below this figure. So you can see that here we try to see what happens if we do not do any rebalancing and if we do it at different points in time. So in our case, if you don't do rebalancing, like in your last 1 hour of training, which can run for a long time, but I think here it was just like a few dozen of hours for like simulation purposes, your throughput can go down by 50% or even more than 50%. But if you do even irregular or like even not very frequent rebalancing, like once every 5 minutes, or potentially you could maybe even go less frequent than that, you can see that the impact is way lower.
Mm.
So you can kind of compensate for that. And of course, there is a very natural extension of this rebalancing strategy where you can move multiple peers between stages at the same time. So for example, if there is a big rebalance between the slowest and the fastest one, you can just move multiple peers between pipeline stages. So if I remember correctly, we even implemented something like that for inference in case of the Petals paper.
Okay. Okay, interesting. And but then in terms of, I mean, convergence wise, how does it compare to like to
Yeah, so this is a very good question, and I think we have some numbers here for figure 4.
figure
Uh,
4?
Here,
7,
page 7.
page 7.
Yeah.
Ah, yeah.
So in principle, most of the modifications I described to you, they do not impact convergence at all, because in principle, it could be made to replicate asynchronous training, sorry, to replicate standard like synchronous pipeline parallelism fully. The only thing we changed is like which peers remain at each stage, and like where do we send the activations between layers. So that was kind of the main change of the algorithm. None of them really impact the training results, assuming that you still do like the same gradient updates after the same number of tokens in principle. So kind of like if you process the given number of examples, batches, tokens, doesn't matter, and you trigger the update and the DDP step in the same way you would do it for pipelining, it's kind of equivalent. We have one specific improvement here to make the procedure more communication efficient. So this one is called one-step delayed SGD, or delayed parameter updates. I think we referenced it somewhere in the paper a bit earlier. But the idea, I'll just describe it very simply, first of all, is that you can keep doing your forward and backward passes even with some staleness of parameters. So let's say that you can keep doing your forward and backward computations for a very big batch if your SGG is delayed by one step. So your parameters are not exactly up to date. But this improvement allows you to basically overlap the communication and computation stages much better, especially in this communication constraint setup, because you can keep processing the previous batches for training in the same time when you are still receiving the gradients for your previous SG step. So as long as it's not that delayed, it basically works in the same way here. So, and the like the impact on convergence for one-step delayed SGD was evaluated by multiple research groups. I think even in Microsoft's zero offload paper, they ran experiments with it, as well as a lot of like theoretical results, which show that you can almost like almost in every set of conditions, you can tolerate this like small bit of asynchronous training.
Okay. And so it seems like it's converging as good as DDP, but and throughput wise, is it like still acceptable or better, or I don't know?
Yeah, so of course, here you would think about the setup in which you evaluate. So we have some numbers in table 3, table 4 in the main paper, and we also have some numbers in the appendix for like standard production ready pipeline parallelism conditions. The thing here is that if you consider like a very standard setting where you do not have any heterogeneity between nodes, where you don't have fault tolerance, and where your like bandwidth is good enough, then you do not need any of that. So
Okay.
I would not say that swarm parallelism is just like the general best approach for pipeline parallel training. Definitely not, because all of the decisions we have to make, and obviously the implementation we had, it's not as well optimized for the set of conditions where everything is uniform and everything can run in the best way, just like orchestrate it once and then leave it be. So definitely not. However, what we observed was that the throughput was actually quite strong. Like if you compare it to the other settings, I think actually it's better to go not in table 3, table 4, now that you think about it, but to the appendix. If you give me 1 second. I think we had something. Just 1 moment.
Mm, which
Yes, I
appendix?
think.
Ah, yeah, it's the page 9. No, not page 9. There was the one table with the GPU utilization. Maybe you're looking for this one.
Yes. One
Oh,
more.
check. Yeah.
Yes, I think it's actually uh in table 2 we had multiple pipelining implementations. Yes,
Ah,
yes, I think that's the one. So
there's table one as well on the left, maybe. Uh,
yes.
Different.
So it's kind of like about different modifications of the algorithm.
Okay.
So I would maybe start with table 2 first.
Okay.
Uh, what we are looking here is different kinds of models. And if you remember the square cube law, we are incentivized to have like as much computation as possible within the same GPU. So layer sharing was super helpful for us here. And if you compare with standard pipelining implementations such as gpipe or 1F1B, which is a particular pipelining schedule, you can see that when there is no latency, definitely like Swarm is not the best approach because you can do a lot better in conditions where you do not have this overhead for rebalancing and some other stuff. We basically took some like PyTorch implementation of gpipe and 1F1B here. However, as you start to introduce latency or even like random latency in your networking, then Swarm becomes a lot more interesting, precisely because of the algorithmic improvements that we've made. And the same thing kind of holds for different sets of conditions when you have no networking overhead versus when you have some networking overhead. I would say that this is the main consideration you need to have in mind when you think about using Swarm or not using it. And of course, if you take a look at table 1, you can also see that like for different kinds of models, which is something that like where swarm becomes more interesting. You probably want to have larger ones, like regardless of the scale, because the GPU utilization will be more consistent over time. Yeah, this is not strictly related to the algorithmic choice, but also something that might be useful when thinking about large scale experiments over like internet scale training with unreliable GPUs.
Okay. So from table one, we can deduce that Swarm is having a better GPU utilization than traditional pipeline parallel.
So for table one in particular, we evaluated not the methods themselves, but the architectures of models, which are
Mhm.
better utilization-wise for different conditions. So this is kind of like us trying to validate the square cube law empirically, if you wish. So
Okay.
let's say that you have like a small model which is run on the same set of GPUs. And because it can finish the same batches faster, like as a simplification, uh, it spends more time relatively on sending those activations over the network. Keep in mind that here we have quite strong bandwidth constraints, like 500 megabits per second. So
Mm.
very slow by regular measures. As you start to increase the model size, however, the picture changes because you need to spend more time on processing the activations relative to sending them because like you have those very big matmoles, like 4 times increase for FFN and then decrease it back, which start to consume more of your GPU time. And the more latency you introduce in your network communications, assuming everything is kind of synchronous, the worse it becomes. And the like improvement or just like jump we had to make here is to go from like standard very big models to big models plus sharing parameters within a particular layer. So I would not say that this is strictly required to apply Swarm, but this was another improvement that we were considering at the moment to make sure that we can train large and like compute intensive models with high capacity while making them leverage even more like GPU time. So in principle, you could do something similar with very like compute intensive optimizers these days, or by applying some other techniques. For example, like doing more compression between layers.
Uh, yeah, okay. I have a question because actually, since we like spend more time computing than communicating, usually people try to compress the activation and or the gradient and then send it over. But here in our case, I mean, we don't need anymore to do compression on the gradient, no, because since it's hidden by the computation in a way, it's like marginal improvement. I mean, in terms of speed, I don't know if you.
It is kind of true, but in principle, and I would say that I think here in the paper, we actually did use 8-bit compression because it didn't hurt the convergence that much for us, like
Mhm,
surprisingly. And also, like, still, you like this is like this numbers in table one, they are for like more synthetic setup and in reality, we found that compression helped a lot in more realistic conditions. We actually evaluated multiple different approaches, like how you can design the architectures to be more compressible, or like which compression schemes you could apply. And we arrived at a very simple observation that 8-bit works well in those conditions. To the best of my knowledge, there were not that many papers which applied compression, like activation or gradient compression,
mhm,
for pipeline parallelism at this point, because pipelining was viewed as something that you do in clusters, for
mhm.
example, and like the communication efficient training community was mostly thinking about data parallel compression. So like techniques like local updates or things like power HDD, where you do low rank approximation of, or like you do like low rank projection of gradients. This is very helpful for data parallelism, but for pipeline parallelism, there were not that many results that we could just use directly. So we had to do a bit of research in that direction.
Okay. Um, I have some questions regarding I mean, as a practitioner, if I were to implement, for example, swap parallelism or just use the repo, there was like some hyperparameters I want to have in mind, like how many nodes like a stage can handle, how many stages, for example, this kind of thing. How do you have like an heuristic or it's just
Um, Yeah, so that's a very good question, actually. And I would say that, especially after our experience with Petals, which was basically a swarm applied to the inference setup,
mm,
I would say that the would be as follows. So ideally, you still want as few pipeline stages as possible because like sending activations, sending anything over the network, really, it takes more time than than it should in those
mm,
conditions. So you can try to use as many, like you can try to put as many stages as possible within the pipeline, and like you can have multiple GPUs use different like chunks of the pipeline, but that's like an over like a more complex version of what we'd have. In reality, just try to use largest like contiguous chunks of
mm.
layers as pipeline stages. That's one thing. Usually, you do not need to rebalance that frequently for adaptive rebalancing. So, like 5 minutes, I think in reality, if your network does not change very frequently, I would say that maybe even a few hours would be a reasonable thing. And for like adaptive rebalancing, I think we even list the hyperparameters, which turned out to work quite well for us. So I think
Okay,
there is like the value that I can refer to. So yeah, I think those would be my main recommendations when applying this
okay,
method.
okay. So I think I will have like pretty much go through the whole paper and the main ideas. Maybe you have like the an idea of like the f further works on Swarm because I saw like some people like Pluralis who started like to implement this as well. So
Yeah. So I would say that in general, the work around fault tolerant and like communication efficient pipelining is far from being done. So we just try to conduct our first range of experiments and like see if that paradigm can be even applied in volunteer conditions. So we had some successful results in that direction. I would say that uh, there are a few directions very interesting to me. So the first one is whether we can do compression like that's aware of the fact that it's applied to activations in particular. So there were a couple of papers on this topic which tried to explore the nature of activations and like how they should be compressible. Because if you take a look at the quantization literature in general, you can see that many methods actually take into account the fact that they are applied to model weights in particular, like specifically. And if you look at, for example, low bit precision training these days, for example, 8-bit or even lower than 8-bit, you can see that sometimes there are different data types for compressing different parts or like different tensors throughout training. So I think there can be some interesting result here to see like what's the best compression scheme for such setups. That is one direction which I'm quite excited about. The other one is about combining this with more asynchronous methods in principle. So the big question is, how can we keep all of the GPUs working all the time, like just busy constantly, without it having too much of an impact on the training procedure itself? So maybe we can do more asynchrony at the data parallelism level. Maybe we can introduce asynchrony at the pipelining level as well. And maybe this whole technique can be combined with techniques like streaming dloco, where you like update different parts of the model based on some schedule. So just like in general, being mindful about the communication constraints is something that would make a lot of impact here if we figured out the correct recipe.
Okay, sounds exciting. There's like so many things to combine.
Yeah, yeah,
Different the level of abstraction. All right. So I think we are pretty much done. Thank you very much. It was like very exciting to hear you explaining the paper because I feel like for most of the people it's quite it's not an easy paper, I would say in general. So it's good to have the authors directly explaining the papers. All
yeah.
right,
Thanks a lot for the invitation.
for sure. So thank you very much and see you, Max.
Thank you.
Bye.
Bye.